Okay, this is the video for Wednesday, and it's going to be on Chapter 9 on searching and hashing. Okay, the searching part, for the most part, we've already covered, and we're going to be covering the two major types of searching we do. Okay, under searching again, we have first the sequential search, and then if sorted, we have the binary search. Okay, so the sequential, and then this been sorted. Okay, we've been through this before. The basic idea is if you have, it could be a linked list, could be an array, whatever your data structure is. Again, you typically wouldn't search a queue or a stack. It's not how those work at all, but you certainly could with a linked list or an array. Okay, but the idea of the sequential search is that you have some series of elements, okay? However those are defined, whether it's a linked list or whether it's an array, doesn't matter, okay? You have to have for your list some key, which is a unique identifier. So if you're dealing with student records, it could be your student ID number, whatever. So you have to know if you found it, okay? So you search for the key in the first array position or the first of the linked list. And you just keep going until either you find it. So, okay, why is that not working? Don't know. Go until either you find the key or you reach the end. Okay. As far as efficiency goes, you could have up to n times to do this. Okay, so if you have an array of 100, you could have to search through all 100 items potentially. Okay, that's the worst case time it could be. Okay, the other kind of search we talk about is a binary search. And a binary search assumes an ordered list, either an ordered array or an ordered linked list, doesn't matter. Okay, but it's this idea that, in fact, this works better for an array because you can get to the middle. If we have an array, okay, then we can go to the middle position and check, is this the key? Okay, if not, we know that every position here is greater than this value. Every position here is less than this value, okay? So for example, if our key is equal to 10 and this X is equal to 7, okay? We know the key has to be found in this direction, okay? So what we do in essence, since we go to the middle, and we'll keep going to the middle, that each step will reduce the possible positions or the possible nodes or values or whatever we have to search by half. Okay, so again, if you have 100 records, we're going to go to that middle position and then immediately wipe out either this half or that half. So then we're down to 50. Okay, so in terms of efficiency, we're going to call this log 2 of n, okay? Because there are records you never, ever have to see, okay? And there's some implementations of both of those in the book that it's worth looking at to see how they're going to operate, okay? They give some examples and all that stuff, okay? So there's no question. So to kind of sum up searching, we have sequential, which has the efficiency, and we call this big O notation of big O of n, okay, up to n times in worst case scenario, where the binary is going to be big O of log 2 of n, okay, which is much less. So the only question becomes, is it worth sorting? Okay. Is it worth making it ordered? It's usually better to keep it ordered if you're going to want to do this, which means every time you add an element, you put it in the right place. And the book talks a little bit about that. Okay. We also have the idea of hashing. Okay. Hashing comes up a lot in computer science. And the idea behind a hashing is you're going to take all of your data and you're going to have a hash function that's going to spit out some hash position, often using the mod. Okay. It's going to use this hash position to store things in a hash table. Okay. So for instance, if we say we're going to use the numerical value of all the letters, A is equal to 1, B is equal to 2, so forth, and we're going to add up all of those values for every word, okay, our hash function then, so our hash table, let's say, is going to have, I don't know, 50 elements in it. Okay, so we can add up the total letter count, that's not the right word, but the total letter positions count. Okay, so A for 1 and so forth. Okay, and then do a mod 50 on it. Okay, so there are a couple of ways to handle this. The first one, and I forget, one's called open hashing, one's called closed, one's called, let's see, chaining's one of them, linear probing, all these things, open addressing. And you can look through the examples as far as that goes, but they're the two basic ways we'll talk about them in theory. You can get the terminology in the book. I've got it here, but it'd take a while to look at. Okay. The first one is going to store linked lists at all these positions. Okay. So in this case, if we have some word that when you do a mod 50, it's going to give us, this position. Okay. This position is then going to become a linked list, however many that it has. Okay. And the idea would be that if you take what you want to look for, okay, and it tells you, well, if it's there, it's going to be in this position in the hash table. You can then look through all the items in that linked list, and you've eliminated all the other ones there. Okay. So that's the basic idea. But it's important to remember that when you do that, when you take all the letters by their position in the alphabet, add them together, and do a mod 50 or a mod whatever, you're going to have what we call collision. Okay. Collision is where more than two values go to the same box. Okay. And that's an issue because we don't want, we have to have a way to deal with it. Okay. So if we were going to have our boxes and not deal with collision, then we have some value, whatever it is, it's going to get a hash function of 3. So we have a 0, 1, 2, 3. So we're going to put that in here. Okay. What if we do another one that also gives us a 3? Okay. Then we can't just boot that out of there. So the linked list is one possibility. And the other way that we can do is this, we're going to put it in the next one. Okay, so then if we go to look for it here, we know to keep looking back to the beginning until we get a blank spot. Then we know we didn't find it. Okay, so those are the two basic strategies that the book talks about for those. Okay, so we know that we're taking basically an infinite number of possible words in this example, and we're going to map it to 50 possible boxes. Okay, so we know for sure that we're going to have collision. Okay, it gets me to one of my favorite principles that we use a lot in computer science, that we know that we can prove it pretty easily. It's called the pigeonhole principle. It states the following, that if you have X number of pigeonholes, Okay, and think here of some kind of a covey or whatever you call it, where you're going to keep the birds. So 4 times 4, I've got 16 pigeon holes here. Okay. It says that if you store more than X pigeons in the holes, what do you know? You know that at least one hole has more than one pigeon. Okay. It could be that all 16 are in the same one. I mean, you can't, we haven't specified one way or the other. Okay. But we know if I put more than 16 pigeons into a cabinet that has 16 holes, I know at least one is going to have more than that. Okay. So if your hash table size is smaller than all the possible things that could come its way, then you know you're going to have a collision, and you have to deal with it either by having a linked list or by having where you move it to the next one. Okay. So hashing gets used a lot. There's some examples they talk about in the book. I'll post some homework problems that do that. Okay. You'll see this again when you take algorithms. We talk about it a fair bit. Okay. But yeah, there's some good examples in there, how the insertion works. There's a implementation using the quadratic probing, which is a different way to do the probing. There's the chaining where we do the linked list, all that stuff. Okay. So again, the issue you always have to worry about here is this load factor. It always comes down to that. Okay. So the load factor, no matter which type of way you're doing things, it's going to be this alpha that we're going to define as the number of records in the table, okay, that you're trying to store in your hash, and then the hash table size. Okay. So again, if you're trying to, and then again, this is called the load factor. Okay. You know, and it's one of those things that the bigger the hash size, the more efficiently it's going to function, but the more memory it takes up. So that turns into a problem. And with these hash functions, even if you're storing 10 records with a hash table of 10, your hash function may not assign those all different ones. So you got to be careful about that. Okay. There's a table of 9.5 on looking at the efficiency of these methods. Okay. And the chaining is the first one I talked about with the linked lists. It's going to have, if it's a successful search, okay, so let's just sum up this chapter here. So we do the chaining. That's with linked lists. Okay. If we find something, the successful search is going to be 1 plus that load factor, which I cannot draw effectively, over 2. Okay. An unsuccessful search will take you up to that load factor. Okay. And then the one where you just looked at the one next to it, that's called linear probing. Okay. The successful rate is 1/2 times, that was a really bad curly bracket, 1/2 times 1 plus 1 over 1 minus alpha for successful. Unsuccessful is 1/2 of 1 plus 1 over 1 minus alpha squared. Okay. Again, we talk about that a lot more in algorithms class, but that's the basic idea. Okay. So we have searches with the sequential search, which starts at the beginning, keeps going until it finds it. And then we have the binary search if we have a sorted list. Now, I may not have said that, I may have started to, but the issue then, oh, I did say it. It's whether or not it's worth doing a sort. How many searches do you do? How much data do you get added? Is it worth the effort to do that? Okay. Okay, so that is chapter 9. So one more chapter this week. I'm probably going to go ahead and do a video. I may do class on Thursday. We'll see what I'm feeling like on Thursday, but we'll see how that goes.